Hello everyone, this is Bolo Joshista from Aerob section. Today I am going to explain about Laplace transforms in mathematics M and MTT. So the founder of the Laplace is the French Newton Pierre Simon Laplace. He developed the mathematics in astronomy, physics, and statistics, began work in calculus, which led to the Laplace transform, focused later on celestial mechanics, one of the first scientists to suggest the existence of black holes. So the one who behind it, the Laplace transform is the Pierre Simon Laplace. So the history of a Laplace transform. Euler began looking at an integral as a solution to differential equation in the mid 1700s. Z equal to integration of x into e power ax dx, where z of x a is equal to integration of 0 to x e power at xt dt. So Lagrange took this a step further while working on the probability density functions and looked at forms of the following equations: integration of x into x e power minus x ax dx. Where finally in 1985, Laplace began using a transformation to solve equations of finite differences, which eventually led to the current transform. So S equal to A into Ys plus B into delta Ys plus C into delta square Ys plus and so on. Ys equal to integration of e power minus s pi of x dx is the formula of Laplace. So the definition of Laplace transform. The Laplace transform is a linear operator that switched a function ft to fs, especially f of s is equal to L of f of t. Integration of 0 to infinity e power minus st ft dt is the formula of Laplace transforms, where s equal to sigma plus I omega. Go from time argument with a real input to a complex angular frequency input, which is a complex. So there are some restrictions in Laplace transform. There are two governing factors that determine whether Laplace transform can be used. F of t must be at least a piecewise continuous for t is greater than or equal to 0. F of t is less than or equal to m of e power yt, where m and y are constants. So continuity. Since the general formula for the Laplace transform is f of s equal to L of f of t equal to integration of 0 to infinity e power minus st ft dt. It makes sense that f of t must be at least piecewise continuous for t is greater than or equal to 0. If f of t were very nasty, the integral would not be computable. So boundedness. The criterion also follow directly from the general definition, where f of s equal to L of f of t equal to integration of 0 to infinity e power minus st ft dt. If f of t is not bounded by m e power yt, then the integral will be not converged. So Laplace transform theory. The general theory of Laplace transforms can be defined as f of s equal to L of f of t, integration of 0 to infinity e power minus st ft dt equal to limit of pi of 8, limit of 0 integration of 0 to pi e power minus st ft dt, where example is equal to f of t equal to 1, where L of f of t equal to integration of 0 to infinity e power minus st 1 dt, where we can take it as a limit e power minus st by st, where pi of 0. Then we can get it as 1 by s. For 1, f of t of 1, we will get 1 by s for Laplace transform. And for convergence e power t square, we get it as infinity. L of f of t equal to limit of pi to 8, where 0 to pi e power minus st e power t square dt, where limit of 0 to pi e t square minus st dt, where we can find it as infinity. So Laplace transform. So there are some Laplace transform, wide variety of functions can be transformed. Inverse transform often requires partial fractions or other manipulations to find a form that is easy to apply the inverse, where L inverse of f of s equal to f of t, where 1 is equal to, for L inverse of f of s equal to 1 by s and e power a t equal to 1 by s a, s minus a, t power n is equal to n factorial by s power n plus 1, t power p is equal to r into p plus 1 by s power p plus 1 sin of at is taken as a by s square plus a square cos at is taken as s by a square plus a square sin h at is taken as a by s square minus s square cos h at is taken as s by s square minus a square and so on. As we can see, these are the normal general formulas for Laplace inverse and inverse Laplace and Laplace transforms. Laplace transform of ODEs, differential equations. The equation with initial conditions like a d square y by dt square plus y equal to 1, where y equal to 0 and y of 0 and y dash of 0 equal to 0. Where we can say Laplace transform is linear, apply derivative formula, rearrange, take the inverse. So we can see L of y of 0 minus y dash of 0 plus L of y equal to 1 by s, where 1 by s into s square plus 1 is taken as 1 by s minus s by s square plus 1, where y equal to 1 minus cos st, since s by s square plus 1 is cos t. So Laplace transform of partial differential equations. As we can see, Laplace transform in two variables always taken with respect to time variable t. Inverse Laplace of two-dimensional PDE can be used for any dimensions. The transform reduces dimension by 1. ODEs reduces to algebraic equation. PDEs reduces to either an ODE if the original dimension is 2 or another PDE. L of u of x of t is taken as u of x of s, that is equal to integration of 0 to infinity e power minus s du by dt. As we can see here, L inverse of u of x of s equal to u of xt, and so on. We can take it as the Laplace can be inversed as the Laplace formula is given. So considering the case where u of x plus ut equal to t, where u of x of 0 equal to 0, u of 0 of t equal to t square, and taking the Laplace of the initial equation leaves u of x plus u is equal to 1 by s square, where the partials with respect to x do not disappear. With the boundary condition u of 0 of s equal to 2 by s cube. Solving this an ODE of variable x, u of x of s equal to c of s into e power minus x plus 1 by s square. Plugging in BC, we can say it as 2 by s cube is equal to cs plus 1 by s square, so that c of s equal to 2s cube minus 1 by s square. U of x of s is equal to 2 by s square minus 1 by s square into e power minus x into 1 by s square. Now we can use the inverse Laplace with respect to s to find u of x of t, that is equal to t square minus e power x minus t of e power minus x plus t. So there, as you can see, the example solutions of a Laplace transform. Diffusion equation, ut is equal to kux in 0 to 1. The initial condition is taken as u of 0 of t is equal to u of 1 of t, that is equal to 1. U of x of 0, that is equal to 1 plus sine pi x by L. And using a of t plus bgt plus and so on, afs plus bgs, df by dt is taken as s of f of s minus f of 0. And nothing that can be partials with respect to x commute with the transform with respect to t. The Laplace transform u of x of s satisfies s of u of x minus x of s minus u of x of 0, where k of x of u is taken as, where e power at is taken as 1 by s minus a and a equal to 0. The boundary condition then becomes u of is 0 of s, that is equal to u of 1 by 1 of s, that is equal to 1 by s. So we can have order differential equation in the variable x together with some boundary conditions. So the wave equation. In Laplace transform, there is a wave equation which is taken as ut is equal to c square uxs, which is the initial condition of u of 0 t, that is equal to f of t, u of x of 0, that is equal to ut of x of 0, that is equal to 0. For x is infinity, we assume that u of x of t is 0 because the initial conditions vanish. The Laplace transform satisfies s square u is equal to c square u of xs, that is equal to u of 0s is equal to f of s. Solving this ODE, we get u of x of s is equal to a into s into e power minus s into s plus bs of e power x by c, where as and bs are to be determined for the assumed property of u. We expect that u of x of s is 0 as x is greater than infinitive. Therefore, b of s equal to 0, hence u of x of s equal to f of s into e power minus x into of s. Now we use x of t of minus b f of t minus b t minus bs f of s to get u of x of t that is equal to h of t. So, real life applications of the Laplace transforms are semiconductor mobility, call completion in wireless networks, vehicle vibrations on compressed rails, behavior of magnetic and electrical fields above the atmosphere, and notation. R is equal to ratio of induced electrical field to the product of the ratio, current density, and the applied magnetic field, where rho is the electrical resistance, H equal to magnetic field, current density, applied electric field, concentration of electrons, U is mobility, where we can take it as Ax equal to rho of J minus Rj of X. So equation manipulation, rho is equal to 1 by n e mu, r equal to minus 1 n by e, and taken as rho of x equal to n e mu 1 plus ux whole square. Then these are the equation manipulations of Laplace transforms. Applying the Laplace transforms is a 0 of minus infinity to, for example, if we take of 0 of minus infinity to e power minus yt sine of x t plus dt is equal to x square by x square plus y square and so on. These are the applications of Laplace transforms. So this is all about Laplace transform. Hope you all understood. Thank you.